Good morning, students. We'll continue our topic in states of matter, and yesterday we are doing van der Waals equation. We'll continue with that. Yesterday we also have done real gases and ideal gases. How ideal gas deviate its path and become a real gas, and how we can correct that equation, that is PV is equal to nRT, which is an ideal gas equation. So the answer is van der Waals equation. We have done in our last topic about the van der Waals equation. The van der Waals applied correction for both the defects. What was these defects, students? The first was the molecular volume, and the second was the molecular attraction. Yesterday we talked about the two inception which was wrong. According to kinetic gas theory, it was been given that it was wrong, right? Which was put by the kinetic theory of gases. And what happened? Van der Waals, who was a scientist, he put forward a modified equation, that is PV is equal to nRT. He modified that equation and named his equation as a van der Waals equation for a state. And this equation is applicable only to the real gases. And it is being given as P plus A n square upon V ka whole square, n upon V whole square, and V minus NB is equal to nRT, where A is constant for the molecular attraction, and also it is known as, students, attraction coefficient. You can see in PV is equal to nRT, we have added the coefficients, or we have added some constant correction factor, rather we can say, right? And this means that if the attractive interaction in this molecule of gas are large, the coefficient A has a large magnitude, and when the attractive interaction in the molecule of other gas are comparatively less, right? This is a significance of A, students. What is the meaning of adding A constant here? This A constant here represents the attractive interaction in the molecule of a gas, which means they are very large, right? And the coefficient A has a large magnitude as compared to the value when the attractive interaction in the molecule of another gas are comparatively less. Similarly, this B, which is a constant, is for the molecular volume, which is also known as co-volume or excluded volume, students. So you must know what is this A and B, and this A and B are the van der Waals constant, right? And this A just resemble, or this A represents the attractive forces, and B represents the excluded or co-volume, right, students? So after adding this constant, we get a van der Waals equation, which was proposed by van der Waals, which is applicable to the real gases only. Now the question comes, what is the significance of these constant, that is A? So A is a measure of magnitude of intermolecular attractive forces within the gas, and B relates to the volume of particles, right? It means here A and B, they are related in this equation. How they are related in this equation? The constant A relates to the magnitude of attractive forces among the molecules. It means greater the value of A, more will be the attractive forces. We can see that the gases like NH3, students, HCl, SO2, they are easily liquefied. The question arises why? This is because of greater magnitude of attractive forces, which is because of the greater value of A, right? Which can be easily liquefied than the gases like helium, hydrogen, and nitrogen. This is because of the value of A, which measure the magnitude of intermolecular attractive forces within the gas. So greater the value of A, the greater will be the magnitude forces. Now, units of A can be expressed like liter square atmosphere per mole. per square mole. Van der Waals constant B. This B represents the co-volume, as I have already explained you, and which is the effective volume of the molecule in the gas. And it is basically, students, 4 times the volume occupied by a gas molecule. So unit B can be calculated with the help of a formula, that is V is equal to NB, or we can find out the value of B. B is equal to V upon N, and the units are, you must know the units, liter per mole, right? Or instead of liter per mole, we can take meter cube per mole. Right, students? I hope you have understood this concept, that why ideal gas deviate, and after deviation, what happened? They just follow, or they behave as a real gas, and real gas do not follow the ideal gas equation. Instead of that, it follows the Van der Waals equation. Now, you must know one thing more: greater the value of A, more will be the tendency of the gas to be get liquefied. So question can come, you have the different gases are given to you, and you have to arrange these gases according to the ease of liquefaction, right? Clear? Now, our next topic is liquefaction of gases, students. Liquefaction means, what do you mean by liquefaction? Liquefaction means how much the gas can be liquefied. So there was a scientist known as the Andrew. Andrew studied the isotherms of different gases. Basically, he studied about the carbon dioxide, and he plot a graph between pressure and volume and keeping temperature constant, right? Isotherms are those only in which temperature are being constant. Now, he observed all the real gases and see that it behave in the same manner as a carbon dioxide. First of all, he only studied about the isotherms of CO2 at different temperature by plotting the graph between pressure and volume. But later on, he observed that all the gases, real gases, behave in the same manner as a carbon dioxide gas. So, after plotting this graph and observing at different temperature the relationship between volume and pressure, he observed two important properties of gases, which are critical temperature and critical pressure. What do you mean by critical temperature, students? The highest temperature at which a substance can exist as liquid, right? Which is being given as TC. TC stands here for critical temperature. And there is a corresponding pressure which is required to bring about the liquefaction at this critical temperature, which is known as critical pressure. So these two terms are very, very important. Along with that, we have a critical volume also. Just we can understand like this. For example, the critical temperature of carbon dioxide is 304 Kelvin. This means that no amount of pressure applied to a sample of carbon dioxide at or above 304 Kelvin. It means 304 is a critical temperature where a gas can exist as a liquid. Above that and below that, it will not be exist in liquid. So this temperature will cause the gas to liquefy, or at or below this temperature the gas cannot be liquefied provided the sufficient pressure is applied. And the corresponding critical pressure for carbon dioxide is 304 Kelvin, is 72.9 atmosphere. It means, students, the application of 72.9 atmosphere of pressure on a sample of CO2 gas at 304 B can be cause the gas to liquefy. So these are very particular terms you must know about it. Next, different in a critical temperature among the gases means that some gases are easy to liquefy than the other. The critical temperature of carbon dioxide is high enough so that it can be liquefied relatively easier at or near the room temperature. By comparison, the critical temperature of nitrogen gas is 126 Kelvin, and that of helium is 3.5.3 Kelvin. Liquefying gases such as nitrogen and helium present much greater difficulty than does the liquefaction of carbon dioxide. And the value of critical temperature of a gas also depends upon its size, shape, and intermolecular forces present between the molecules of the gases. When a gas measures its critical temperature, its critical pressure, then at that stage, the volume of that gas is called critical volume, which is represented as Vc, and the critical volume of oxygen is 74.42 centimeter cube per mole. That of carbon dioxide is 95.65 centimeter cube per mole, and that of hydrogen is 64.51 centimeter cube per mole. Right, students? So critical temperature, what is the significance of critical temperature? The critical temperature for different gases help us in comparing the relative tendency of a gas to get liquefied, right? So greater the critical temperature, the easier is the liquefaction of a gas. Properties of liquids: vapor pressure, boiling point, viscosity, and surface tension. These are some of the general properties you might have heard in your physics class also about the vapor pressure, boiling point, viscosity, and surface tension. So what is vapor pressure, students? In liquid, the pressure exerted by the vapors when the rate of evaporation becomes equal to the rate of condensation, right? Or we can define it in another way that vapor pressure is a pressure applied, right? Vapor pressure is a pressure exerted or applied by the vapors of a liquid in equilibrium with a liquid at a given temperature. Now, what are the factors on which vapor pressure depends, students? Nature of liquid, right? How it is being linked. If the magnitude of the intermolecular forces present in its molecule are weak, the molecules will readily change into vapors, right? And the second one, it means the higher the vapor pressure of a particle liquid, lesser will be the magnitude of these forces. Second is the temperature. The vapor pressure of liquid increases with the rise in temperature. How? When the temperature is increased, the average kinetic energy of the molecule also increases. As a result, what happens? The number of molecules have sufficient kinetic energy to overcome the intermolecular forces of attraction, which also increases, and this lead to greater number of molecules in a vapor phase. So you must know, as the temperature increases, vapor pressure also increases. The second is the boiling point. What is boiling point? The vapor pressure of a liquid increases with the temperature, we know that. And at a particular temperature, if the vapor pressure become equal to the atmospheric pressure, that temperature is known as boiling point. As we know, the boiling point of water is 100 degrees Celsius. Right, students? Surface tension. Now, what is surface tension? Surface tension is defined as a force acting per unit length perpendicular to the line drawn on the surface of a liquid, right? Or we can say the tangential forces acting along the surface of a liquid, which is at the right angle to the surface along 1 centimeter length of a surface. This is a technical definition basically. And that surface tension is a property of a liquid, students. And the surface tension depends upon the temperature of the liquid and the nature of the liquid. How? Surface tension decreases with the rise in temperature, because as temperature rises, the kinetic energy of molecule also increases, and this results in a decrease in the intermolecular forces of attraction, also decreases the surface tension. And nature of liquid, the surface tension of liquid is linked with the intermolecular forces of attraction. So greater the magnitude of forces, more will be the value of surface tension. For example, water has a greater surface tension as compared to alcohol, as compared to ethers, right? So many question comes like, why the raindrops are spherical in shape? This is because to reduce the surface tension, right? Why they have a spherical in nature, or why insects can walk on the surface of water? What is a capillary action? These type of question can arise on surface tension. Next is viscosity. It is a frictional force, friction basically, between the two layers of liquid moving past one another with different velocity. Viscosity means, students, what do you mean by viscosity here? For me, what is viscosity? Viscosity means concentrated, right? When the things are concentrated, that is called viscous. Viscous means gada, right? So viscosity here stands for the frictional force between the two layers. If I talk about the water and oil, which is more viscous in nature, which will take less time to flow. So less time kaun lega? Water. So viscosity basically the force applied per unit area, right, between the two layers of liquid with the different velocities. And what are the factors? Temperature, as well as the nature of liquid, as well as the molecular mass, students. Temperature has an inverse relationship with rising temperature. The viscosity decreases. Nature of liquid, as there are the stronger molecular forces of attraction, the viscosity of that substance will have more, right, as compared to the other. And molecular mass, viscosity of liquid generally increases with the increase in mass, students, right? So these are some of the properties of a liquids. Thank you so much.